Scientists theorized that we all come from the same place, even if the term place is ambiguous in this case. We should say we all come from the same singularity. According to the Big Bang model, the matter in our bodies is billions of years old because nothing existed before it, and all that exists comes from it, even us. But what triggered the Big Bang? Keep watching till the end of the video to find out. The answer might shock you. First, saying that the Big Bang is a theory could be misleading. For those who are not used to a scientific language, the word theory means a system of hypotheses capable of coherently explaining a large number of observations. Theories are taught because they represent the state of the art of our knowledge on a given set of phenomena. They are always open to improvement, but they are the best we have at the moment. If you hear someone saying, "It's just a theory," it doesn't mean anything. It would be like asking, "Why do we teach basketball?" since it's just a set of movements. We teach it precisely because it is a set of movements to which we attribute a corporal, social, and cultural value. In fact, the Big Bang is the predominant model in the scientific community based on astronomical evidence and observations. It is a cosmological model based on the idea that the universe began to expand at very high speed in a finite time in the past, starting from a condition of extreme curvature, temperature, and density, and that this process continues to this day. According to most astrophysicists, all the matter found in the universe today, including the matter in people, plants, animals, the Earth, stars, and galaxies, was created at the very first moment of time, thought to be about 13 billion years ago. The universe began, scientists believe, with every speck of its energy jammed into a very tiny point. Everything in the known universe was compressed into a dot smaller than an atom. This extremely dense point exploded with unimaginable force, creating matter and propelling it outward to make the billions of galaxies of our vast universe. Astrophysicists dubbed this titanic explosion the Big Bang. The Big Bang was like no explosion you might witness on Earth today. For instance, a hydrogen bomb explosion, whose center registers approximately 100 million degrees Celsius, moves through the air at about 300 meters per second. In contrast, cosmologists believe the Big Bang flung energy in all directions at the speed of light, or 300 million meters per second, a million times faster than the H-bomb, and estimate that the temperature of the entire universe was 1,000 trillion degrees Celsius at just a tiny fraction of a second after the explosion. Even the cores of the hottest stars in today's universe are much cooler than that. So, the Big Bang is observed truth, but some details haven't been quite worked out. There are a lot of things that may have happened, and we may need different theories to explain those, or maybe we don't have an explanation at all. In fact, science isn't about being right all the time, it's also about being wrong. If everything was perfectly known, science would lose its intrinsic meaning. There's another important quality of the Big Bang that makes it unique. While an explosion of a man-made bomb expands through the air, the Big Bang did not expand through anything. That's because there was no space to expand through at the beginning of time. This means that if we were sitting on the singularity when it happened, we would have been incinerated, but we wouldn't have heard any bang. But now the point is, every explosion has an ignition point and a center of the explosion. What about the Big Bang? Let's suppose you're on a date and you go out and look at the sky. Suddenly, he or she asks you to point where the Big Bang happened. Well, my suggestion in this case would be to immediately leave, because there is no central point. There is nowhere in the sky you can point and say, that's where the Big Bang was, because the Big Bang was everything, and it happened on the moon, it happened on the sun, it happened in your bedroom, it happened everywhere. Also, at the Peach epoch, the universe was only a tiny fraction of a second old. In fact, it was even tinier than a tiny fraction, 10 to the 36 seconds old. From there on out, we have a roughly decent picture of how the universe works through physical laws. Prior to the Big Bang, however, our understanding of the universe gets a little bit fuzzy. The forces, energies, densities, and temperatures become too high, and the knowledge of physics we've cobbled together over the centuries just isn't up to the task. In the extremely early universe, gravity starts to get very important at small scales, and this is the realm of quantum gravity, the yet-to-be-solved grand riddle of modern physics. We just flat out don't have an understanding of strong gravity at small scales. To put it in different words, at small enough scales, we don't know if the word before would even make sense. At incredibly tiny scales, and we're talking tinier than the tiniest thing you could possibly imagine, the quantum nature of reality would break our neat and predictable concept of space-time. Notions of intervals in time or space don't really apply at those scales. We can't know for sure what's going on, but we can make some suppositions. For example, in a new paper that appeared in November 2019, researchers detailed the mechanisms that could cause the Big Bang explosion, which is key for the model that scientists use to understand the origin of the universe. In particular, they define the specific criteria where we can drive a flame to self-generate its own turbulence, spontaneously accelerate, and transition into a hypersonic detonation. The key is applying the right amount of turbulence and mixing to an unconfined flame until it becomes self-perpetuating, at which point the flame begins to burn the ingested energy, leading to a hypersonic supernova explosion. There are, of course, other theories that attempt to describe what ignited the Big Bang, but at this stage, most of them are pure speculation. During the 1920s and 30s, Edwin Hubble discovered that the universe is expanding, with galaxies moving away from each other at a velocity given by an expression known as Hubble's law, V equals h times r. Here, V represents the galaxy's recessional velocity, r is its distance away from Earth, and h is a constant of proportionality called Hubble's constant. The exact value of the Hubble constant is somewhat uncertain, but it is generally believed to be around 70 kilometers per second for every megaparsec in distance. This means that a galaxy 1 megaparsec away will be moving away from us at a speed of about 70 kilometers a second, while another galaxy 100 megaparsecs away will be receding at 100 times this speed. So essentially, the Hubble constant sets the rate at which the universe is expanding. Since the universe is expanding, we can intuitively observe that, at a certain point in the past, everything must have been squeezed into a tiny volume. If we manipulate the Hubble's law, we can see that the age of the universe can be assessed by reversing the Hubble constant. For a Hubble constant of 100 kilometers per second, we get about 10 billion years. This is how we can calculate the age of the universe. But the details of what specifically caused the Big Bang still remain obscure. Trying to explain the birth of the universe is not a simple task, but we trust that our scientific curiosity and new discoveries will lead us to a deeper understanding of where we come from and where we're going.